this section could have been two small sections. It actually used to be in older editions of the book. But they were both so small, they just said, hey, we'll put them together. One section talks about complements. Of course, we already talked about complements. And the other section talks about conditional probability. And actually, we talked about both of these ideas a little bit already, but it's going to give us a little bit more detail, I think. So what's the rule of complementary events? Well, here it is, right? What do I mean by a complement? I mean that the probability of A plus the probability of A complement has to equal 1. Although this is not the version you usually write when you use it. When you use it, usually you know one of them and you're trying to figure out the other one. So like, if I know the probability of A, I might use this version. The probability of A complement is 1 minus the probability of A. You guys saw me use this, right? What would you do if you knew the probability of A complement and you wanted to know the probability of A? Yeah, that's also a rule, right? These are all in your book. But, you know, that's the rules we've been studying. I'm going to go quickly. Here is the thing we want to study now. You're going to see problems in your book where we say, hey, what's the probability of at least one happening? So, example. Suppose it rains 20% of the time. What is the probability of getting, 20% of the time is not, I'm going to say 20% of the days in this town. What is the probability of getting at least, there's the words at least, 1 day of rain over the next 7 days? And this is a question you could think about for a minute and talk to someone next to you, and maybe you can make an estimate. If there's a 20% chance of rain, what is the probability of getting at least 1 day of rain over the next 7 days? How about I ask you this? Do you think it probably will rain over the next 7 days, or probably won't rain over the next 7 days? How many say it probably will rain over the next 7 days? How many say it probably won't rain over the next 7 days? And how many don't want to vote? Let me ask that. There we go. See, this is not easy. If I say there's a 20% chance of rain on any given day, suppose I say there's a 20% chance of rain today. Do you think it's going to rain? I'm hearing no's, because 20% is less than what? 50% would be a 50-50, a half. It might not. 20% we're saying, oh, probably not. What's that? But there's 7 days here. That's the thing. It might rain at least once, maybe twice. I guess it could rain all 7 days. Would you expect that to happen? Could it happen? Could, but not likely. Go ahead, Julie. Oh, yeah. It says it rains 20% of the days in this town. I guess 20% on any given day that it's going to rain. And you're right. I'm not very clear here. And I don't care, because the weathermen aren't very clear either when they say there's a 20% chance of rain. Honestly. And honestly, as a mathematician, this bothered me for a while, because they weren't being so precise. And I wanted to know, how did they get that figure? And now I'm not so bothered about it anymore.
I
I don't know. But I guess I'm not quite as bothered. I'm thinking it's not as much of a classical probability thing anymore as I used to think. Okay? It's more of they're trying to communicate to you whether or not they think it's going to rain. If they say 20%, well, their butt's covered if it rains, but they don't think it's going to rain. If they say 90%, they're pretty sure it's going to rain, but if it doesn't, they're still safe, right? This is what I gather. Now, what is the probability of getting at least one day of rain? Well, this is the point of this chapter. We are studying complements. So my question is, if I let A be the event that it rains at least one day, what is A bar? Well, it's an event that, what happens? It doesn't rain at least one day. Can we say that a different way? That it rains. If it doesn't rain at least one day, less than one day is true. But if it rains less than one day, 0 days, right? It doesn't rain. I claim that that is an easier probability to determine. What is the probability that it rains 0 days? Well, let's look at it this way. What's the probability that it doesn't rain today? 80%. What's the probability that it doesn't rain tomorrow? Now, I have to be a little careful here, because what did I just do? I multiplied, right? And is that true? Am I allowed to multiply whether it rains today or whether it rains tomorrow? I'm only allowed to do that if I know that those events are independent. And in all honesty, they're not. Right? If it rains today, it's more likely it'll also rain tomorrow. It might carry over. Big storm. This is why maybe making up an example is not the best idea. Okay. Scrap this, guys. Put a big X through that. Because I realize now I can't multiply those. It'd be nice if I could. Nevertheless, at least I got across the big idea. A bar is the event that it rains 0 days. That might be easier to compute. And in the examples we're going to do, oh, there we go. The complement of getting at least one item of a particular type is that when you get no items of that type. So let's move ahead. I'd like to look at problems 16 and 18 from your book. Those are nice. There I'm not going to run into problems. So, page 176. I don't know. Because I told you those are not independent. That's why I said put an X through it. But we'll go to problem 16. This I can do. I'm not a weatherman. In China. This is an interesting problem. You guys should read this. Read problem 16 to yourself. They tell me that B is the event. I'm going to let B be the event that a boy is born. And so the probability of a boy is 0.5845. 58.45%. So most of the time, well, more than half anyways. More than half of the time a boy is the baby that's born. So you take a family in China, and so each individual couple can only have one child. Let's say you have a group of relatives and there are 5 babies. The question is, what is the probability that there is at least one girl? So if we want to compute the probability that there is at least one girl out of 5 babies, this will equal the probability that what happens? Well, let's think of it this way. What's the complement of this event right here? So it's going to be 1 minus the probability that what happens? What's the complement of having at least one girl? It's the probability of 0 girls. That's right. 0 girls out of 5 babies. Now, if there's 5 babies, I can assume that for each couple, those are independent events, right? The sex of my baby doesn't influence the sex of your baby, etc. Comments, David? That's the point I was trying to make in the last slide. When I was talking this stuff about rain, I was trying to figure out the probability of getting at least one day of rain, right? The complement of that is that you get no rain. So this at least one, this is the key idea of this. The complement of at least one is none. Because at least one means 1, 2, 3, 4, or 5 in this case. But the complement of that would be none. Yeah, Scott? Yes, one girl or more. Right. That's right. So, we get 1 minus. Now, I have to compute the probability of 0 girls out of 5 babies. And so here I'm going to use the multiplication rule. Okay? And I'm going to do, well, the chances of the first one being a girl, oh no. Here, let me write it this way. Let me write it this way. 1 minus, this probability is also the probability of getting 5 boys. Right? It's the probability of getting 5 boys. So, 0 girls means you got 5 boys. So this is going to be 1 minus. Now we know the chances of getting 1 boy are 0.5845. But the chances of getting boy, you'd have to multiply those together by the multiplication rule. Because remember, 1 boy and another boy and another boy, right? And another boy, so the and tells me to multiply. And another boy. So that's really what you want to type in your calculator. Except that, of course, you algebra people know that there's a shortcut. How do I multiply over and over again? I'm going to write 0.5845 to the what power? That's what I'm really going to type in my calculator. Okay? Jim, let me finish and then I'll take your question. But just to get the actual value, let me go ahead and type in the calculator. If I clear this out. First of all, let me take 0.5845. This caret key means raised to the power. It's right above my divided by sign. And I'll put a 5. Oh, look at that. So now if I do 1 minus my answer, I got 93%. Okay. So what does that mean? 93.1 or 0.9317. I should do it like you guys are supposed to. 0.9318, let's say. So the probability of getting at least one girl out of 5 babies is a 93% chance. Is this okay? Oh yeah, let me show that again. So I had 0.5845 caret 5, right? And then I wanted to do 1 minus that. So I typed in 1 minus, and I wanted to get the answer to reappear. And see it says ANS right above the negative sign? You could hit the second key, and then hit that ANS, that negative sign, and it shows up. So there's 93%. (93% of the time, you'll get at least one girl out of those 5 babies. It says, can that system continue to work indefinitely? What do you think? Yes? What are they trying to get at here? Everyone wants boys. So what could happen if the system keeps going forever? There might not be enough girls in the population years from now to continue the population. That's the concern. Okay? So this is a social sciences issue at this point. Yeah, Noah? Oh, okay. David? Wouldn't be, right. These are good questions. Scott? The point was to try and downsize the population, but I'm not sure it was to make the population mostly male. So it's interesting. Okay. Problem 18 might be worth doing also. Let's see, problem 18. According to FBI data, 24.9% of robberies are cleared with arrests. That means, okay, we solved the crime. A new detective is assigned to 10 different robberies. What is the probability that at least one of them is cleared with an arrest? So probability again of at least one arrest. How are you guys going to do a problem like this? You'll do 1 minus the probability of what? 0 arrests. Yes? No, we did the subtraction already. We subtracted 7 and got 93. Okay. So 1 minus the probability of 0 arrests. So let's see. How would I get 0 arrests? Well, 1 minus I'm sorry. I didn't write this correctly. It's not at least 1 arrest. It's the probability of at least one case cleared with an arrest. I mean, yeah, I guess it's okay what I did before. So this equals 1 minus the probability that no cases are cleared with an arrest. Now, according to FBI data, the probability of a case being cleared is, what did they say? Okay, so I'm going to write that as 0.249. So what's the probability of a case not being cleared? One minus what? 0.249. So that's 1 minus 0.249. I guess it's 0.751, right? So this is going to equal 1 minus 0.751 raised to what power? 10th. Because we need all 10 of those cases to not be cleared. So at this point, I'm just going to get a figure for you. Right there. One minus 0.751 caret 10. This will do the 0.751 to the 10th power first, and then it'll do 1 minus what you get. So I got 0.943, or 0.9429. 94.3% if you want. Now, that's part A. Part B says, what's the probability of the detective clearing all cases with arrest? So, all 10 cases cleared. Can you guys tell me what that would be? You're going to take that 0.249 to the 10th power. Now, if I do that, oh, what's that mean? E to the negative 7. That means times 10 to the negative 7. What it really means is move this decimal point 7 places. Now you have to decide, do you move them to the left or you move them to the right? Well, is this a big number or a small number? It's a really small number. So I'm going to move them to the left 7 places. So I'm going to get 0.000000912 or something like that. It's a really small probability that he's going to clear all 10 cases, according to this statistic. What if he does clear all 10 cases? What would you conclude? Super cop. Well, better than average, right? Much better than average. So that's right. That's the right conclusion there.